Good afternoon, everyone. So, today we are going to discuss uh, another kind of energy conversion device, which is known as fuel cells. So, this fuel cell is very similar to uh, like a battery, like electrochemical cell, where you convert again a chemical energy to electrical energy, as well as you also create or you generate some heat, and the byproduct is water in this case. And that is why this is one of the, like right now, one of the alternative source of energy which can provide a green and environmental friendly energy source. And how does it work? So the working principle is again similar to the uh, to electrochemical cell. So as shown here in the figure, what we have here is electrode, so which are immersed in some kind of electrolyte. So it's a electrolyte membrane, and these electrodes. So in a typical electrochemical cell, everything is kind of closed. Okay, so everything happens within a closed box, so to say. So like in batteries, but here one needs to provide the fuel from an external source. And in this case, in fuel cells, typically hydrogen is used as a fuel, and this hydrogen, sorry, so hydrogen goes in here. So at the electrode, it will dissociate and will form hydrogen or proton or hydrogen ion plus electrons, and these protons will move through the electrolyte towards the cathode, and simultaneously at the cathode you also provide some fuel, or so not fuel, so in this case it is air or maybe oxygen. Normally it should have oxygen in the content. So this oxygen will uh, so this is the second, the cathode electrode, where the oxygen will be reduced and will combine with hydrogen, and the electron which is flown out in the outer circuit, so they will combine and form water as a byproduct. And that is why this fuel cell is, so here you see you take a fuel, quite clean fuel you are consuming, so hydrogen and oxygen, and in the process you get electricity and the byproduct is water. So instead of like carbon dioxide in other cases, in case of fossil fuels. And as I said, so this is again very similar to a electrochemical cell, just like a battery. And again, you have both oxidation and reduction reaction taking place at the electrode. And this is a redox reaction that is happening at the electrode. And that is how, so again, you have a flow of the ions through the electrolyte, but the electrons will flow outside in the outer circuit, and that is how you can convert your chemical energy in this dissociation process. You can convert your chemical energy to electrical energy. So the reaction, as I said, so at the anode, so typical reaction is you have hydrogen which dissociates to proton and two electrons, and these two electrons will flow in the external circuit, and this proton will move through the electrolyte to cathode, where it will react with oxygen and the two electrons which are coming from the outer circuit, and they will form water. Okay, so the net reaction is basically hydrogen and oxygen will combine to form water. And this is why it is one of the green technologies and quite actively being pursued for energy conversion processes. So typical cathode and anode material is what is used is platinum, and electrolyte, there are different electrolytes that are used, and therefore the fuel cell, there are various fuel cells that we will discuss in a couple of minutes. But the cathode or the anode material where is basically platinum, and this uh, platinum is used as a catalysis here. Okay, so uh, by uh, by using this platinum as a catalyst, so uh, you can make sure that this dissociation of hydrogen molecule can happen quite fast and efficiently. So this conversion from hydrogen molecule to a proton can happen, and these electrodes act like the catalysis which helps in this process. So, what is the basic mechanism here of this? How you convert these molecule into these ions is basically what you have is adsorption of the molecule on the electrode material. So, for example, these molecules will get absorbed on platinum, and then they will dissociate, okay, and then they will be transported across the through the electrolyte from one electrode from the anode to the cathode. So here in this figure, yeah, so this is a figure where oxygen, this how oxygen reduction is taking place. This figure shows here. So what happens, like you have the cathode material and oxygen will get adsorbed, and then it dissociates. So this adsorbed oxygen will dissociate, and uh, it can capture the electron, and also it can react with other ionic species, for example hydrogen, and then uh, so this oxygen can also move through this electrolyte as well. So these mechanisms are like pretty much like one of the reason why so there is a reason why this oxygen will be adsorbed on the surface, okay, and uh, it may not adsorbed on all the surfaces of a material. So it is not like, so this oxygen will adsorb on certain surfaces, and that depends on the what is the crystallographic orientation or which plane. So for example, if you have less number of the density of the atoms in those planes are less, so probably oxygen can get adsorbed there. It also needs that there can be some defect sites or voids where oxygen can get trapped and get so this is again also true for hydrogen as well. So both the hydrogen and oxygen, so they get dissolved on the electrode material, and they have to break, and these electrodes basically provide a quick path for the electron to flow. So that's why these ions, and again these ions have to move through this electrolyte from one end to the other end, and when they combine, so they will form this water. And therefore this mechanism is quite extensively actually studied. What is the reason these molecules will get adsorbed, and what kind of surfaces uh, will help in this adsorption and dissociation process. So it is not like all the surfaces, the crystallographic surfaces will be active or reactive in that sense. And therefore a lot of modeling happens uh, in this field actually. So what is the exact way these molecules are getting uh, getting attached to the surfaces and how they break and so on, and how this diffusion takes place. So sometimes the diffusion happens on the surface, sometimes through the bulk, and that is where a lot of investigation material. So which kind of electrode material will lead to this, or can do this efficiently? So that is where a lot of modeling happens. But so far, platinum has been used almost like in all fuel cells, although there is a like there is a need to change platinum. So we will discuss that later on. But this is basically a mechanism how this molecules get converted from neutral species to a ionic species. So as I said, there are several types of fuel cells that exist in the that one can find. So the most one of the first and most used fuel cell is this proton exchange membrane fuel cell. So in the short form, it is known as PEMFC. So proton exchange membrane fuel cell. So the kind of fuel cell is again depends on what kind of fuel is used and what is the electrolyte that is used. So basically that tells you the difference between what kind of fuel cell, uh, or what is the kind of fuel cell that we are talking about. So the difference, so the kind of fuel here is hydrogen and air. So hydrogen will be injected to the anode so that this hydrogen or the proton will form. So hydrogen will dissociate, and electrode normally platinum, most of the cases platinum, and this electrolyte in this case is a solid Nafian membrane. It's like a polymer membrane that is a solid electrolyte that is used, and you get output voltage of 1.23 volt. And normally the operating temperature is about this 350 to 400 Kelvin, so quite high. And typical efficiency again depends on the design of the fuel cell, but typically like yeah can vary quite a lot, but mostly like around 40 to 50% the average efficiency that you get in this fuel cell. So the second kind is this alkaline fuel cell, so AFC. So where everything like remains the same like before, but now the electrolyte has changed to potassium hydroxide. So this is an alkaline material, and again the voltage output will be pretty similar because the chemistry and the thermodynamics, everything is quite similar, and the output voltage of the cell will be the same, operating temperature also nearby, and efficiency also very similar. Only what you have changed is the electrolyte material. So then the third kind is a direct methanol fuel cell. So what is so here in this case the fuel is different, methanol. Although the electrolyte you can use mostly the same, like for this here. So this solid Nafian, this membrane is normally used. So in this proton exchange membrane fuel cell, so very similar to that, but the fuel is methanol. And the reaction then definitely will be different at the anode side. So now instead of hydrogen, what we have is uh, methanol, and this will react with, and then you also need water as well, and the reaction will lead to again, you need a hydrogen production so that this hydrogen will go and react with oxygen at the cathode, and this electron again will move through the outer circuit, and then in this reaction again in the cathode the reaction is exactly the same. The output voltage a little bit less, but typically in most of these fuel cells, you get of the order of 1 volt, so not more than that. And again, operating temperature is like about 360 to 500 Kelvin, and efficiency is 40%. So then the fourth one is a phosphoric acid fuel cell. So again, the name tells you what kind of electrolyte is used in this fuel cell. So this is a phosphoric acid that is being used in the electrolyte, which is quite corrosive in nature. But typical performance also, like the output voltage, again very similar. Operation temperature also about 500 Kelvin. Efficiency also very similar. So, and the fifth one is a molten carbonate fuel cell, where this lithium carbonate or potassium carbonate is used as an electrolyte. And electrode is typically nickel can also be used. So platinum is preferred, but nickel in this case can also be used. This is all based on the what kind of chemistry that can happen or that is going to happen at the electrode. And moreover, you can use different fuels as well. So here you can use hydrogen, you can use uh, carbon monoxide, methane, you can also use other hydrocarbon gases as well. So the fuel can, you can use more number of different kinds of fuels. And the reaction, what is happening is this carbonate will react or will help in the dissociation of hydrogen. Uh, and one of the product here is carbon dioxide in this fuel cell. So which is undesirable, but it so if one wants to use these fuels, this hydrocarbon, so carbon byproduct will be definitely there, and you get this carbon dioxide as a byproduct, which is not desirable. And also you have a high operating temperature as well. So the sixth one is a solid oxide fuel cell. So this is one other. So this proton exchange, proton membrane exchange fuel cell is one of the mostly used fuel cell. The first one we looked at, and this solid oxide fuel cell is also one of the most investigated fuel cell right now as well. So here, what is the electrolyte? It is either solid zirconia, okay, so zirconium oxide or yttrium oxide that is used as an electrolyte, or maybe sometimes this a composite of yttrium and this yttria and zirconia, this yttrium oxide and zirconium oxide is also used. So which is so the short form is YSZ. So typically that is also used as electrolyte, and the operating temperature is 1300 Kelvin, very high, and efficiency is the highest amongst all the fuel cells. So it is about 55 to 60%. So one of the highest efficiency this oxide fuel cell, solid oxide fuel cell has. So all these, so different fuel cells have been designed and shown to, I mean, with reasonably good efficiency, they are being manufactured. But mostly, what is the two most popular one is the solid oxide fuel cell and this proton exchange membrane fuel cell. Okay, so these are the most studied or investigated fuel cell. And but also nowadays this direct methanol fuel cell is also kind of has attracted some attention. So one of the reason is so normally when we talk about hydrogen production, like we will talk about that maybe in a couple of lectures later. So hydrogen production and storage. So here we are using hydrogen as a fuel. Okay. So this is how one can produce this fuel, hydrogen. So that is uh, actually a challenge. Okay, so how you produce or generate hydrogen, and then how you store hydrogen. So that is actually a big challenge in fuel cells actually. And methanol, direct methanol fuel cell is advantageous because you don't go through the products. So normally sometimes you get hydrogen from methanol actually. And so in this, so if you use methanol directly as a fuel, so you can get hydrogen, so without really, you don't have to convert methanol to hydrogen separately and then bring it to your fuel cell. And that is why this direct methanol fuel cell is actually nowadays also gaining a little bit more attention from industry as well. Okay, so these are the different kinds of fuel cells, but like, so these fuel cells, of course, like one can use it for mostly people are talking or thinking to use it in automobiles. Okay, so for vehicle propulsion, so you can use it in cars, trucks, or I mean, the first use of fuel cell actually happened in when this space mission, so NASA used it. They used it for basically I mean, for propulsion purposes, like in 1960s, in 1960s 70s they used for like Apollo and this spacecrafts, when they used to send, they used these fuel cells. uh, but after that, kind of the use for, like, they can be used, I mean, people are predicting, so they can be used uh, for all kind of automobiles. So starting from car, your or ships, I mean, they can be used in mostly in the transport sector quite a lot. However, there are many challenges that still remain, which is kind of interesting from the research perspective, and which has, I mean, why they are still not that popular, or they have not replaced, let's say, battery in that way. Although, if you look at the solid oxide fuel cell, or this proton exchange membrane fuel cell, PEM cells, they are the the byproduct is always water, so which is really good for the environment. And that is why a lot of effort is now being given to to reduce. So one is like they have really quite high cost. Okay, so why the cost is high? Because they use this platinum electrode material. So when you use this, platinum is very expensive, also a rare material. It is not that abundant on earth. So therefore, uh, one needs to change or find an alternative electrode material. But why platinum is so popular is, this is like one of the best, like one of the noble metal that acts as a best catalyst. Okay, so why it acts as a best catalyst? Because it is non-reactive, so it is not really reacting to the chemical processes that is going on the surface. Okay, so that is why it will have a long life. And it is also, so it will not degrade or corrode due to presence of water. So you have water, you have humidity, you have temperature. So you can think these electrodes can degrade, other metal electrodes will degrade quite fast. And that is why platinum is actually preferred. And but again, although it has the best performance in terms of as an electrode material, but it is very expensive. And that is why there is a lot of effort going on, like what kind of electrode materials one can use, so that you can replace platinum and use with the same efficiency. So you can keep the efficiency of the fuel cell intact, and you can also operate it at high temperatures, because most of these are operating at higher temperature. So another challenge is like in terms of supplying the fuel. So most of the cases what we saw is the fuel is hydrogen. So how you can supply it efficiently and in a environmental friendly way, okay, without really a, because production of hydrogen is also a challenge, and how you can store it. So if you want to use it in a vehicle and you want to put a cylinder of hydrogen as a fuel, so sometimes it can be dangerous as well. So there is chances of explosion of hydrogen if there is a leakage. And if you use some other fuel, so like for example we saw where different hydrocarbon gases are used, or methanol is used, so what can happen is you have undesired byproducts. So carbon dioxide can be one, but also you can have other byproducts which get deposited on your electrode material. Okay, so if they get deposited on the electrode material, so your catalytic properties of the electrode material will degrade, and that will again affect the efficiency of the fuel cell, as well as the life cycle of the fuel cell. And that is why one needs to supply a fuel efficiently. Also, sometimes in the fuel, what happens, it is not a clean fuel. So what do you, if you take hydrogen, so it can be mixed maybe with some other corrosive gases, which can also react to your electrolyte, it can react to your electrode, which is not desirable. So you also need a clean fuel, 100%, almost 100% hydrogen. And that is why this is another challenge that needs to be addressed. And we will talk about this hydrogen, so particularly generation of hydrogen and the storage in maybe after one or two lectures. Okay. And another limitation here is of the fuel cell is a high temperature operation. So it is operating at relatively high temperature. So if you talk about this SOFC, solid oxide fuel cells, so they have the best efficiency, okay, but operates at 1300 Kelvin, which is, which is it doesn't matter for the conversion process as long as we are getting the electricity out of it in a safe way. But that also limits the kind of electrode materials one can use. Okay, so you can imagine, so the electrode materials should have a good electrical conductivity at that high temperature. So you cannot use a normal metal as an electrode in that solid oxide fuel cell, because the conductivity, electronic conductivity will be low, so it will decrease. And as well as it should withstand this temperature for a long period of time, because fuel cell, when you are using as a conversion uh, device, so you want to use it for a longer period of time. So you are driving a car or a vehicle or a aircraft, so they should be, you can use it for a longer period of time. And that is why this high temperature is a challenge, so operating it at a high temperature. And that is why a lot of effort is also going on to particularly in this solid oxide fuel cell design, so to use materials which can, or use alternate electrolytes, okay, which can operate at a relatively lower temperature. And also you can design your uh, electrodes in such a way so that they can withstand, even if they are working at a relatively higher temperature, so still they will keep their structural integrity and the properties which is desired, like the catalytic properties or their mechanical properties, so they should not crack or break due to this high temperature operations. So these challenges we will address. Yeah. So one another thing is this interesting. They have an interesting current voltage relation. So that means the cell voltage, how it varies when you are, if you want to draw more current from the cell. So in the beginning, of course, so you have like a so you have a small current, you are drawing a small current, and it starts with all the chemical processes. So this conversion from hydrogen to proton, and this diffusion of hydrogen through the electrolyte, or diffusion of proton through the electrolyte, and all this starts. And so the cell voltage is quite high and you draw a very small current. But as the equilibrium, this chemical equilibrium is attained, so normally it really acts like a normal ohmic conductor. Okay. So this is, so most operation will happen in this ohmic region. Okay, so this is very like similar to your resistance, what you observe in voltage VI IV curve. And then if you want to draw more current density, so what happens is there will be a reduction in the efficiency of conversion of your gas to ions. Okay, so the conversion, this mm, chemical process of conversion from your fuel, from your neutral hydrogen to proton, happens with certain efficiency. So if you want to draw more current, so this conversion efficiency will be reduced, and then voltage will of the cell will drop. Okay, so this is a typical IV characteristic of the fuel cell, uh, and which is let's say normal in that sense. So, and as you can see, so mostly what you have is you have uh, like a theoretical voltage. Normally you get 1 volt, but then due to this different resistance and so on, so you lose the actual voltage output of the cell. But typically it is about very close to 1 volt. And therefore also sometimes you may not use one single cell. So this is the IV characteristic, one of the single cell. So you have to use many cells in series or in parallel, depending on the application. And that is also where how you can manage their the voltage output by using many number of cells. That is also a management which is necessary in this fuel cell. Okay, so this is about the fuel cell, different kinds of fuel cells. But to address these challenges what I described here, so we will look at the impact of nanotechnology or nanomaterials, how they can help in addressing these challenges. So we will look at that aspect tomorrow. Because like as we saw in case of batteries, the electrode materials, so how nanotechnology or nanomaterials are really helping in terms of increasing or having new electrode materials that can be used in a battery. So similarly we will see what kind of nanomaterials or nanostructuring, how it can help in addressing these challenges tomorrow.